My name is Joseph Azevedo, and this is my lab report for Lab 5. In this report, I'm going to go over the purpose of the lab, the fundamental physics principles involved, the procedure involved, and the analysis performed at each stage, where I modeled a bar magnet falling through an aluminum tube to take 0.4 seconds, which was within 10.05% of the observed time, and finally, some follow-up questions about the lab's contents. So, starting off, the purpose of this lab was to experimentally verify the effects of Faraday's law on the motion of a falling bar magnet, and to apply our knowledge of kinematics and magnetism to create a computational model that predicts the velocity and position of the bar magnet as it falls throughout time. Throughout the lab, we're going to rely on a handful of fundamental physics principles, namely, Faraday's law, which states that the time-varying magnetic field generates voltages in a conductor loop, which will in turn create its own magnetic field that affects the original source, the Biot-Savart law, which gives the magnitude and direction of a magnetic field caused by an electrical current, the definition of magnetic flux, Ohm's law, which relates the magnitude of the induced current versus the EMF, and finally Newton's first and second laws of motion, which relate the velocity and net force acting upon an object. The procedure for this lab is fairly simple, and involves using a small bar magnet and a roll of aluminum foil. First, the dimensions for the aluminum foil are noted, including its length and inner and outer radius. Second, I used a magnetometer app on my phone to note the north pole of the bar magnet. Afterwards, I prepared my experimental setup, which involves setting up the aluminum foil vertically and readying a video camera on my phone to record the setup. Finally, I dropped the bar magnet through the roll of foil a total of 5 times, recording the entire time. When the bar magnet is dropped in the foil, it ends up falling observably slower than if it was in near free fall, and the electromagnetic interactions that cause this are the focus of the rest of this lab. Note that the choice of using an aluminum foil roll is significant here, as it is non-ferrous. This is because a ferrous material such as steel can have its resistivity impacted by the magnetic field itself, which would add significant error to the measurements. Anyways, the measured values from the experiment are shown here. The dimensions of the aluminum foil roll have been noted, and the average time it took for the bar magnet to fall to the bottom was calculated to be 0.360 seconds. Finally, the magnetic dipole moment of the bar magnet was calculated using the same procedure from Lab 3 involving a magnetometer and a ruler, and the final value was determined to be 3.08 ampere meters squared. Now that I obtained the measurements, the second part of the lab was the analysis, where we developed a conceptual model to explain the behavior and make predictions. The reason that the bar magnet falls slower than it would in free fall is because it creates a changing magnetic flux throughout the aluminum foil, which, in turn, according to Faraday's law, will create an induced current. Then, due to the Biot-Savart law, we know that the induced current will create a magnetic field of its own, and when we calculate the magnetic force applied on the bar magnet due to this field, the force ends up opposing the force of gravity. As a result, the net force, as the magnet falls through the aluminum foil roll, is still pointed downwards, but with a smaller magnitude than it would be in free fall. This causes the acceleration of the magnet to be slower, and with that, it takes longer to fall through the tube. In order to actually model this phenomenon, we turn to GlowScript, which lets us rapidly develop a computational model. Now, because much of the code was provided in the lab materials, I'm going to give a brief overview of only the code that I actually wrote, though the full code is available at the link in the description. First, I include experimental measurements taken during the procedure discussed earlier. Then, I define helper functions to calculate both the magnetic field of the bar magnet and the time derivative of the magnetic flux. Third, I modify the simulation loop code to calculate the induced current using the magnetic flux time derivative and resultant magnetic field for a bunch of small slices of the aluminum foil. Finally, I included code to determine the net force acting upon the bar magnet and step forward the simulation according to the delta time. The model predicts that the time it would take for the bar magnet to fall through the roll of aluminum foil is 0.4 seconds, which places it within 40 milliseconds, or an error of 10.05% when compared to my observed average time of 0.36 seconds. This difference is ultimately likely due to the impurities in aluminum foil and inaccuracies in the various measurements taken. Now that I've covered the procedure and results of the lab, I wanted to touch on a few follow-up questions. First, if the resistivity of the conductor were reduced as close as possible to zero, then the capacity for it to conduct would be greater, and as a result, the magnitude of the induced current and its resultant magnetic field would increase. Ultimately, this would cause the bar magnet to take longer to fully fall through the tube. On the other hand, if holes or slots were cut into the tube, then this would reduce the amount of conductor that could experience an induced current, and would overall reduce the capacity of the tube to experience an induced current and slow down the magnet. As a result, the bar magnet would move through the tube faster. In conclusion, in this lab, we experimentally verified the effects of Faraday's law on the motion of a falling bar magnet, and we applied our knowledge of kinematics and magnetism to create a computational model that predicted the bar magnet to take 0.4 seconds to fall through the foil, at a percent error of around negative 10.05% compared to the observed time.